Welcome back everyone. In this lecture we will actually continue to study uncountable sets. So first let us actually look at what happens to the Cartesian product of finite limit 0 comma 1s. So we want to understand uncountable sets. For that the motivation indeed actually comes from understanding first the Cartesian product of this 0 comma 1. So recall this is exactly you take this two element sets 0 comma 1 and then you take n copies of them and then take the Cartesian product among them. And in particularly given any element a bar, so that looks like a sequence, so which you can denote it by a tuple like a naught, a1 etc. a n minus 1. So this is how the typical element is written. So now what we want to do, we want to actually make a connection with this Cartesian product to any power set of A where A has n elements. So let us fix a set capital A which has let us say exactly n number of elements. Let us list them as x1 etc. xn. So we have labeled the elements of this capital A and then we have listed them as x1 etc. xn. So now what we are interested in? We are interested in the power set of A. So by definition you collect all possible subsets of this capital A. So you collect all S such that S is subset of this capital A. Note that empty is there and all other subsets are there. So now we want to actually understand like what will be the cardinality of this power set of A. To understand that we will relate that with this Cartesian product of n copies of 0 comma 1. And it is an easy exercise to see that if we take the Cartesian product of this 0 comma 1 n copies, then the number of elements in that set will be exactly 2 power n number of elements. So more generally, so this is well known, suppose A and B are two sets. So assume that both are non-empty sets to make Cartesian product meaningful. Then the cardinality of A cross B is going to be exactly, so let us only assume the finite sets. Okay. Then the cardinality of A cross B is going to be the cardinality of A times cardinality of B, which is Nm. Okay. So using that one can easily conclude that the cardinality of 0 comma 1 power n is going to be exactly 2 power n. Okay. So we want to say that the power set of A is also has exactly 2 power n number of elements. So how one do that? We will explicitly find out a bijection from this power set of A to this 0 comma 1 power n, that Cartesian product. So we take power set of A and then define this map, call it F, which is a map from power set of A to this 0 comma 1 power n. So what we are going to do? So you fix a subset S of A. Now we know that this S is also listed among this x1 etc. xn. That means we can actually write this x as S as xi1 etc. xik, where what we have done, we have chosen this i1 etc. ik coming from this 1 to n. Okay. So now from this what we are going to do, we are going to associate actually element in 0 comma 1 power n. So the way we want to do that, so we actually take this n boxes, okay, because any element in 0 comma 1 power n is going to be a this n tuple which contains 0 or 1. So that means we have exactly n boxes from 1 to n, and then all we need to do is we have to fill 0 1 inside this 1 comma n boxes. So, if you think about it, a subset S actually determines some indices which are exactly given by I1 etc. Ik. So, then we will be able to identify where those I1 etc. Ik they are living inside this 1 comma n. So, then what we can do, we need to say that the corresponding xi corresponds to I in S belongs to this S. So, that means we can actually simply put 1 there in those boxes, and then remaining boxes we can put 0. So, that is going to give us actually an n tuple inside 0 comma 1 power n. So, basically what we have done, we have constructed this L of S. So, L of S consisting of this A I, which is a sequence or n tuple, where A I is given by either 1 if I is in S or 0 otherwise. So, now this association that we have actually defined, which is goes S goes to this L of S, it is not very difficult to see. This actually defines a bijection from the power set of A to this 0 comma 1 power n. So, this is indeed a bijection. So, this is something I am not going to prove now, I will leave it to you to check. This is something very simple to check. So, what matters is the map actually. So, it is actually different way of thinking what will be the subsets of S. So, basically we can actually think this L of S as indicator function of this S. Basically it takes value 1 whenever I is in S, otherwise it takes value 0. So, I have already told you one way to think about a tuple is that one can think that as a function from 1 to n to 0 comma 1. So, a tuple A bar is also a function from this 1 to n to 0 comma 1, 0 comma. So, that means like this actually indeed what we have done is actually we have defined this indicator function of this S, and it is not very hard to see that indicator function completely determines this capital S. So, that way we get a bijection from this power set of A to this 0 comma 1 power n. And this is something one can generalize, that is why I did this baby case. So, now if we are actually replacing this n by for example natural numbers, then we will be getting something better. So, that is where our first uncountable set that we are actually getting. So, what we are going to do, we take this 0 comma 1. Now, instead of taking finitely many copies of Cartesian product of 0 comma 1, we will take actually countably infinitely many copies of 0 comma 1 and their Cartesian product. So, this means we have this 0 comma 1 times etc. times 0 comma 1 and then times etc. So, this is what we are taking. We are taking countably many infinite product of this 0 comma 1, and any typical element A bar is going to be a sequence which is denoted by A0, A1, A2 etc. Now, note that all these AIs, they are all coming from 0 comma 1. So, it is either 0 or 1. So, now how do we actually visualize this? So, like what we did earlier. So, for a n element set A, we identified this power set of A with this 0 comma 1 power n. So, now that is what we are going to do it here as well. So, here we have taken like this capital N copies of 0 comma 1, and then we have taken the Cartesian product of that. So, it is natural to expect that the power set of n will be bijectively corresponds to this set 0 comma 1 power n. So, that is what we are having. So, we have this power set of n, and then from that to 0 comma 1. So, we will be able to define this bijection capital F. The way we are going to define this capital F, which is very similar to what we have done before. So, we pick a subset S of n and then we associate this L of S. So, now L of S is given by a tuple AI, where AI is going to be given by, it is exactly 1 if I comes from S and 0 otherwise. And this function is going to be a bijective function. So, this capital F is a bijective function. since it is a bijective function, that immediately tells you that these two sets, power set of n and 0 comma 1 power n, they are indeed have same cardinality. So, this implies 0 comma 1 power n and the power set of n. So, they have same cardinality, and we will prove in a minute that they are indeed uncountable. So, they cannot be countable. Okay. Okay, so let us actually verify the details why this is indeed a bijective function. So, one way to look at it, if I start with S, which is subset of n, then this S can be listed again. So, this S can be actually written as I1, I2, I3 and so on, where I1 will be less than I2 will be less than I3, etc. So, now it could be finite set or infinite set. So, depending upon that, so we will get either finitely many these ij's or we get infinitely many these ij's. So, now what we are going to do? So, we are now instead of taking this finitely many boxes, we will be taking actually infinitely many boxes here. So, what we will do, this is 1, this is 2, this is some n plus 1 and so on. So, we think this tuple as a as filling in these boxes. So, then you can see that so we will have like I1 at some place and then I2 at some place and so on. So, then all we are going to do is we will just fill them with the number 1 inside those boxes. Okay. So, the remaining boxes we fill it with 0. So, that means we got a sequence or tuple A bar inside your S. So, which is what we called it as L of S. So, we got this L of S which is this filling. Okay. And it is easy to see that these fillings actually determines this I1 etc. I1, I2 etc. this capital S, elements of capital S. So, that means this association S goes to this L of S is indeed a bijective function. Okay. So, indeed it is easy to define what will be the inverse map. So, the inverse map is defined as follows. Suppose if I start with A bar, which is the tuple AI, I in n. So, what will be the inverse F inverse of A bar, which is a subset capital S, which is defined to be you collect those I in n such that AI is exactly 1. Okay. So, this is my inverse map. So, since I have given inverse map very explicitly, so using this one can check that F is indeed a bijection. Okay. So, this actually proves that the cardinality of power set of n and this 0 comma 1 power n, they have same cardinality. So, now let us actually look this 0 comma 1 very closely, power n. So, this is we are going to say that this is indeed uncountable. Okay. So, what if not? So, if it is actually countable, then what happens? So, suppose that this set 0 comma 1 power n is indeed countable. If it is countable, then what we can do? We can actually have a surjective map or even so it is obvious that this is infinite. So, then we will have actually a bijective map from n to 0 comma 1 power n. But anyway, we do not need actually bijective map, it is enough to have a surjective map. Let us say F is a surjective map from 0 comma 1 to n. So, then there exists surjective map from n to 0 comma 1. So, this is indeed surjective. So, since it is surjective, the image of this F is going to be entire 0 comma 1 n. So, that tells us that one will be able to actually list all the elements of 0 comma 1 power n. If it is not bijective, the listing actually some elements could repeat, but it does not matter. So, we will just list all of the elements. So, this tells that the elements of 0 comma 1 power n can be listed as follows. Let us call the listing as A naught bar, A1 bar, A2 bar and so on. So, all the elements can be listed using the natural number. So, you have A naught bar, A1 bar, A2 bar, they are all just the image. So, basically AI bar is exactly given by the image of I, okay, for all I in here. So, now we have this listing. Now, using this listing we need to actually arrive a contradiction, because we want to prove that it is indeed uncountable. So, how do we proceed? So, let us actually list all the elements properly. So, this A bar naught, this is going to be a tuple again. So, let us list them as A naught naught, A naught 1, A naught 2 and so on. So, now you can see that where I am heading, I am going to use Cantor's diagonalization technique again. But here Cantor diagonalization actually used in the counting all these elements, but here somehow I need to actually come up with an element which is not in the list A naught I. Okay. So, basically that is what we are going to do. So, we are going to find some B bar which is an element in 0 1 n, such that this B bar cannot be an element in this A naught bar, A1 bar, etc. So, that means this is the image of F. So, that tells you that you cannot have a surjective function from n to this 0 comma 1 power n. That proves that 0 comma 1 power n must be uncountable. So, this is what we want to do. So, for that we are going to list all the elements. So, let us list it as follows. A bar, A naught bar is A naught naught, A naught 1, A naught 2 and then A1 bar is A1 naught, A1 1, A1 2 and so on. So, likewise we are listing all the elements. So, A bar n will look like A n 0, A n 1, A n 2 and so on. So, now how are we going to actually define this B bar, which is let us say B naught, B1 etc. So, I need to just tell how the B naught is defined. Okay. So, if you think about it, what we can do, so we can look at all these tuples and then we can actually look at the first row of this infinite matrix. So, now you can see that the very first element. Okay. So, to make sure that this B bar is different from A naught bar. So, it is enough to actually make sure that one entry of B bar is different from one entry of A naught bar. So, for that purpose what we will do, we will take this 0 0 entry. So, we will look at this 0 0 entry and then what we will do, we choose actually B naught which is different from A naught naught. Okay. So, that option is there because A naught naught is fixed, A naught naught is going to be either 0 or 1. For example, if A naught naught is 0, so then we choose B naught to be 1 and similarly if A naught naught is 1, then we choose B naught to be 0. Okay. We can always choose the remaining element because there are two elements in the given set 0 1. Okay. So, that way we can make sure that B bar is different from A naught bar and this is something I can do for all elements. So, to make the procedure more rigorous, so like I said, so to actually differ from this A n bar, it should differ only at one place. So, what we will do, we will just look at this nth place which is A n n. Okay. So, there we choose this B n which is different from A n n. Okay. So, that is what we will do. So, for example, in A1 bar we choose this B1 which is different from this. Similarly, we choose Bn which is different from this. So, that way we actually make this sequence B bar and the way we constructed B bar will be different from all this a bar n for all n in n. That is because b bar n, the nth place will be different from the nth place of this n a n bar. Okay. So, because of this we will have this b bar is different from a n bar. So, that tells you that we got an element b bar which is from 0 comma 1 power n, such that this b bar is not an element in the image F. So, that means the original assumption that we have a surjective map is indeed not true. So, that proves that 0 comma 1 is indeed uncountable. And now we have a bijective function from p of n to and this 0 comma 1 power n. So, because of this you can see that p of n is also uncountable. And it is not difficult to actually prove that the cardinality of this 0 comma 1 power n is same as the cardinality of closed interval 0 comma 1 and the cardinality of the real numbers. So, maybe I will leave it as exercise. I will just outline how one can go about it. The cardinality of 0 comma 1 power n is same as the cardinality of the interval 0 comma 1 and which is same as the cardinality of the real numbers. Okay. For example, how do you go about this 0 comma 1? So, what we can do, we can actually use the binary expansion of the real numbers. Okay. That will actually tell us that you can have a bijection from this. For example, if I start with x, so then I can write x in terms of the binary expansion of x. So, then you will be able to actually get a map from the close to 0 comma 1 to this 0 comma 1 power n. Okay. So, this is indeed injective map. So, that is so the way you want to actually write down. So, you write x as so there will be some sequence x 1 etcetera x m. So, this is the okay. So, because 0 comma 1 we are only talking about 0 comma 1. So, the binary expansion of this will not contain any the integral part of it. So, the 2 square and all cannot appear. So, everything has to be actually should start from 0 point etcetera. So, since x is coming from this, so if you actually recall the binary expansion of x, then so if we take x from actually 0 comma 1 and when x equal to 0 or 1, it's their binary expansions are very clear. So, now if x is actually coming from actually 0 and 1, so then it is not difficult to see the binary expansion of this is going to look like 0 point some a 1, a 2 and so on, where these ai's will come from 0 comma 1. Okay. So, one can actually write this sequence as starting from a naught also, there is no issue. So, maybe one can write it as a naught, a 1, a 2 and so on. So, now the map is very clear. So, you take any x and then you send it to this tuple a I in n. Okay. And that is going to actually give us, of course, so what will happen to this? Okay, maybe like we will treat this as a naught. So, just to avoid the confusion. So, this is going to be written as a naught dot a 1, a 2, a 3 etcetera. All these ai's will come from 0 comma 1. And when x is actually between 0 and 1, then a naught will be 0 always. Okay. And when ai is actually coming from this 0 comma 1 for sure. Okay. And it is not difficult to see binary expansion is actually unique. So, this map actually going to be injective map from closed 0 comma 1 to this 0 comma 1 power n. So, now you may actually wonder how to actually get the very explicit bijection, and if we actually modify this bit then we will be able to get a bijection. But I am going to actually prove a theorem which actually going to be very helpful, and that theorem actually going to tell us it is enough to actually get injective functions from, so from A to B and B to A to guarantee that both have same cardinality. Okay. So, this is the most important result in set theory, which says that, which is the Schroder-Bernstein's theorem. So, let me state it. So, which actually talks about how to compare two sets. So, you start with A B being two sets, and then assume that you have an injective function from A to B, injective function from A to B, and then you have another injective function from B to A. So, then we can conclude that there exists a bijective function from A to B. That means that in this case we can say that cardinality of A is same as cardinality of B. So, basically what we want to say indeed that whenever there is an injective function, then the cardinality of A we want to say this is less than or equal to cardinality of B. And similarly, when we say this there is an injective function from B to A, then the cardinality of B less than or equal to cardinality of A. So, basically we want to say that if this is happening, cardinality of A is less than or equal to cardinality of B and cardinality of B is less than or equal to cardinality of A, then we want to conclude that cardinality of A is same as cardinality of B. So, here I have told you have an injective function from 0 comma 1 to 0 comma 1 power n, and it is not difficult to actually come up with injective function in the other way. So, then that would tell you that that the cardinality of these two sets must be equal. Okay. So, this is this Schroder-Bernstein theorem. This is actually true when A and B are finite sets. So, now we are not dealing with finite sets anymore, we are actually dealing with any given cardinality sets. So, that is why like one should be actually very careful in proving this. So, this is such a nice result which is actually useful in proving. The proof is not very difficult, proof uses little bit of fixed point theory, which I will explain what it is. So, now once we have this theorem, you can see that many of these things can be proved easily, because all we need is we need to actually, if you are interested in for example, comparing the cardinality of 0 comma 1 and R. So, then it is enough to actually get an injective function from R to this closed 0 comma 1, because we already have this inclusion which is gives you injective map. So, that means the cardinality of closed 0 comma 1 must be at most the cardinality of R. So, now if you are able to find an injective function from this R to close 0 comma 1. So, then we are actually indeed done. So, if you think about it, it is not actually difficult to find functions like this using analysis. Okay. Maybe I will actually leave it to you to think about it. So that once you have this injective function, this is already there for free, and that will tell you that the cardinality of R and cardinality of 0 comma 1 will be same. Okay. So, even though the closed 0 comma 1 looks like a much smaller set than this R. So, here they have the same cardinality. So, that is the most interesting part. Okay. Similarly, this can be used in other sets that we have encountered before. For example, we can prove that Zx will be countable, and then all algebraic numbers, for example, inside either real field or complex field, they will be countable and so on. So, one can use this theorem in many places wisely, and then compare the cardinality of given two sets. Okay, so I will actually prove this theorem in the next class. So, this requires little bit of preparation, which is not very hard. The abstract ideas, if you are seeing it for first time, you may find it difficult, but the ideas are not very hard. Like one can actually use little bit of fixed point theory to prove this Schroder-Bernstein theorem. Okay, I will stop here. We will continue in the next class. Thank you.